Hello everyone, this is Dr. Vivek Laha and today we are going to discuss about the algebra of the simplex method. In our previous lectures, we have seen that we can solve a linear programming problem with two variables using graphical methods. We find out the corner point feasible solutions of the feasible region. Then we evaluate the values of the objective function at each and every corner point feasible solution. And then we compare the values by which we get the optimal solution of the linear programming problem. We have also seen that it is possible to find out the optimal solution of the linear programming problem without actually calculating the value of the objective function at each and every corner point of the feasible region. Now we will use the same concept algebraically to find out the solution of the linear programming problem. First, we change the given linear programming problem into a linear programming problem with equality constants, and we call it augmented form of the linear programming problem. So we change this inequalities into equalities by adding some new variables x3, x4 and x5, which we call as slack variables. Now we write this equation as maximization of z subject to z minus 3x1 minus 5x2 equal to 0, x1 plus x3 equal to 4, 2x2 plus x4 equal to 12, 3x1 plus 2x2 plus x5 equal to 18, where all these variables are greater than equal to 0. So we consider this objective function as one of the constants. Now, if we substitute these two variables x1 and x2 equal to 0, then we can find out the value of other variables also. So we substitute x1 and x2. So here x1 0, x3 will give you 4, x2 0, x4 will give you 12, and x1, x2 0, x5 will give you 18. So these variables are known as non-basic variables, which we equate to 0. The variables x3, x4 and x5 are known as basic variables, and the solution, which is initial basic feasible solution, or we can also call this as augmented corner point feasible solution, because it is corner point feasible solution of the augmented linear programming problem, and this corresponds to the value 0 0 of the original problem. That is corner point feasible solution 0 0 of the original problem. Now once we have this solution, we have to test the optimality of this solution, and we can see that the objective function is z equal to 3x1 plus 5x2. Now since x1 is equal to 0 and x2 equal to 0, and these are the non-basic variables, we can increase the value of x1, which will increase the value of the objective function z. We can also increase the value of x2, which will increase the value of objective function z. So this solution is not optimal. Okay, this solution is not optimal. Now we will see that how we can increase the value of either x1 or x2. So the objective function is z equal to 3x1 plus 5x2, and we can see that if we increase the value of x1, the value of z will increase by a multiple of 3, and if we increase the value of x2, the value of z will increase by a multiple of 5. So we must increase the value of x2 so that it will increase the value of the objective function more than in case of x1. So we call it as entering basic variable. So the entering basic variable will be x2. Now once we have this entering basic variable x2, we can find out the leaving basic variable as well, because x2 will enter the basis with respect to some variable which will be the leaving basic variable. So see, this old non-basic variable is x1 because x2 is entering the basic, but x1 will remain as a non-basic variable. So what we will do, we just substitute the value of x1 equal to 0, so it will give you x3 equal to 4, this one. You have this x1 equal to 0 here also, so it will give you x5 equal to 18 minus 2x2. See, x5 equal to 18 minus 2x2, and here we will have x4 equal to 12 minus 2x2. Now these variables must satisfy the non-negativity constant. So these variables must be greater than equal to 0. So once these variables are greater than equal to 0, we can see that this x2 will be less than equal to 12 by 2, that is 6, and x2 will be less than equal to 18 by 2, that is 9. Now since this x2, if x2 is less than equal to 6, it will also be less than equal to 9. So we have to take the minimum out of both the values so that both the constants must satisfy the non-negativity condition. So once we have this x2 equal to 6, x4 will become 0, and hence it will be the leaving basic variable. Okay. So leaving basic variable is x4, and once we have this leaving basic variable, we have entering basic variable as x2, and we have this leaving basic variable as x4. So the value of the column corresponding to x4 must be replaced by the columns corresponding to x2. So what we will do, see, the columns corresponding to x4 here x4 is the coefficient of x4 is 1, and otherwise the coefficient is 0 throughout. So what we have to do, we have to just have the coefficient of x2 here 1, and throughout it must be 0. So if we want the coefficient of x2 to be 1 here, what we have to do, you just divide this equation 2 by 2, so it will have a new set of equation 2, that will be x2 plus x4 by 2 equal to 12 by 2, that is 6. Now once we have 1 here, see here the coefficient of x2 is 0 plus 0 x2. So we don't have to do anything. This one equation number 1 will become equation number 1. Here you can see the coefficient of x2 is minus 5. So if you multiply this equation number 2 by 5 by 2 and add it to 0, suppose we multiply this equation number 2 by 5 by 2 and then add it to 0, then that will give you a new set of 0 equation. And here also we need 0, so what we have to do, you just have this equation number 3, just subtract equation number 2, and then we will have a new set of equation number 3. So if we do all these Gaussian eliminations, we will have a new system of equations with us, and this new system of equations, if we substitute, now we can substitute these values. If we substitute x1 equal to 0 and x4 equal to 0, x1 equal to 0 and x4 equal to 0, so it will give us the solution. This x3 will be 4, see, this x3 will be 4, and x2 will be 6, and x5 will be 6. And what will be the value of this objective function? The value of the objective function will be 30. Okay, now what we have this new basic feasible solution, and the value of the objective function at this new basic feasible solution is 30. Now our aim is to find out whether this new basic feasible solution is optimal or not. So you see that this is the objective function, this is the new objective function, and here you see the non-basic variable x4. If you increase the value of x4, the value of the objective function will decrease. If you increase the value of x1, the value of objective function will increase. So hence x1 will be the entering basic variable. So what about the leaving basic variable? So we just substitute value of x4 0 everywhere. we substitute the value of x4 0 everywhere, and we have this new set of equations as we have already calculated in the previous iteration, and it will give us the value of x1 is less than equal to 4, and here it is less than equal to 2. So we will take the minimum value which will decide the leaving basic variable. So it corresponds to x5. So the leaving basic variable will be x5. So now we have to do the Gaussian elimination as we have done in the previous iteration, so that we can find out a new set of equations. So this is the Gaussian elimination, because these are the basic variables. We have done this Gaussian elimination, and then we can substitute the value of x5 equal to 0 here. X5 and x4 must be 0, so we will have this value x3 equal to 2, x2 equal to 6, and x1 will be equal to 2. So this is the new basic feasible solution, and the value of the objective function will be, so this x4 and x5 equal to 0, so the value of the objective function will be 36. Now again we have to test whether this basic feasible solution is optimal or not, and we can see that this is the objective function z equal to 36 minus 3 by 2 x4 minus x5. So if we increase the value of x4, the value of the objective function will decrease. If we increase the value of x5, the value of the objective function will also decrease. So this is our optimal solution. There is no way of increasing the value of the non-basic variable so that the value of the objective function increases. So this is the optimal solution. Now so this we have the augmented optimal solution as x1 equal to 2, x2 equal to 6, x3 equal to 2, x4 equal to 0, x5 equal to 0, and the value of the objective function is z equal to 30. So the corner point feasible solution related with the original linear programming problem is x2 equal to 2, x2 equal to 6, and z equal to 30. So in this way we have evaluated the optimal solution of the linear programming problem by using algebraic method. Now what are the conclusions? The original LPP can be changed into an augmented linear programming problem. Then we equate the non-basic variables to 0 to evaluate basic variables. We test the optimality of the initial basic feasible solution. If it is optimal, then we stop. Otherwise, we decide the entering basic variable by maximum increment in the value of the objective function. We decide the leaving basic variable by minimum ratio test. We evaluate the new basic feasible solution by Gaussian elimination, and we repeat the procedure till we obtain the optimal solution. So now once we have done all these algebraic procedures, we will, in the next lecture, we will see that how we can use all these informations more systematically in a tabular form, and we can solve a linear programming problem using simplex method. Thank you for joining.